Welcome everyone for this new SIPTA seminars. I'm happy to see that many people to attend our talk of today, which will be given by Christoph Jansen on decision making and robust statistics and machine learning. Now I will just hand over the microphone to Georg Kollmeier that will introduce our speaker, Christoph Jansen, in details, and will handle the scientific part of this seminar.
Welcome everybody. My name is Georg Kollmeier. I'm from Munich and I'm a collaborator of Christoph Jansen, our today's speaker. First, let me introduce Christoph. He studied mathematics and statistics at LMU in Munich. And then from 2015 to 2019, he made his PhD under the supervision of Thomas Augustin at the working group Methodological Foundations of Statistics. Then, after a short interruption where he worked as a math teacher, he came back to LMU, and then from 2021 till now, he is a postdoctoral researcher at LMU. And now he is at his final stages of finishing his habilitation. So I'm very thrilled to hear what's going on. And now I want to say something about his research interests. You will hear most of these stuff in his talk, I would think. The main focus he's working on is decision theory, and especially in the context of imprecise probabilities. So to say, imprecise probabilistic information. And the other aspect he is working on is that he looks at the same time at situations where also the utilities are, in a sense, imprecise, or to be more precise, not of a cardinal scale of measurement. So he looks at utility structures which are of ordinal scale of measurement, or something between ordinal and cardinal scales of measurement. For this, he introduced his genius concept of what he is calling a preference system. You will hear, I think, about this in a few seconds. And beyond this, in technical terms, he is using order theory and lattice theory. And on the computational side, he uses linear programming techniques to solve these decision problems. And I think he is talking today about decision making under such weakly structured utility settings. So with this, I want to finish, and I want to hand over to Christoph. And please, the stage is yours, I would say.
Thanks again, Georg, for the nice introductory words, and thanks the organizers for inviting me. So I'm very excited to be given the opportunity to speak here on decision making under weakly structured information with two applications, one to robust statistics and one to machine learning. So Georg did most of this already, but let me nevertheless give some introductory words about myself. So my name is Christoph Jansen. I'm a member of Thomas Augustin's Foundation of Statistics group at the Department of Statistics of LMU Munich, where I'm currently about to finish my habilitation. And from June on, I will be an assistant professor at Lancaster University, Leipzig. And my first contact with SIPTA is now, I think, 10 years ago in the 2014 edition of the summer school in Montpellier, where I just found out that Sebastian is currently located. And currently, I am an at-large member of the SIPTA Society. Okay. Yeah, and then to the outline of my talk. The first part will be about what I consider to be the basic model of decision theory. The second part will be about how we can extend this model to also address information settings which are weakly structured. The third part will be about how can we utilize this framework of decision making under weakly structured information for problems of statistics and machine learning under non-standard data. And I will exemplify this by two applications, one on inference for non-standard data and the other for statistical multi-criteria benchmarking of classification algorithms. Okay, the first part, basic decision theory. I think probably all of you are familiar with this, but just to give us some common vocabulary to talk about, the basic model of decision theory under uncertainty always involves some agent who has to choose among different acts, which we denote by capital letters, from a known set calligraphic G of those acts. The challenge is that the consequence of choosing an act depends on a state of nature, and we know the set of all possible states of nature, but we do not know the state of nature in advance. And a bit more formally, the formal model of decision under uncertainty involves a consequence set A, which formalizes the consequences the different acts, choosing the different acts could yield. And then each act is simply a mapping sending states to consequences. And our decision problem, calligraphic G, is a subset of this set. Yeah. And the abstract goal in decision theory is to determine some choice function. So a function sending sets of acts to subsets of those acts, which formalizes the selection process of selecting optimal acts among those or non-neglectable acts among those. And of course, the goal should be to that this choice function is not constructed arbitrarily, but in a way that best possibly utilizes the available information. And speaking about information, the interpretation, the concrete interpretation of the choice sets of a choice functions, of course, heavily depends on the quality of the underlying informations. And there are, I think, two different interpretations of these choice sets. One could be the strong interpretation. Then the choice sets are interpreted as equally optimal acts from the inserted set. And the point is, among those acts in the choice set, the agent is indifferent, and each of the sets in the choice sets is strictly better than is better than the acts outside the choice set. So we have indifference, and under the weak interpretation, the choice set is only interpreted as a set of non-neglectable acts from given the information. And the difference is that here the agent is only the acts in the choice set are only incomparable for the agent, but there's not an indifferent structure. And obviously, if we deal with weakly structured information, we will often have to make do with only weakly interpretable choice functions. But before turning to this in more detail, let's briefly list two very prominent choice functions under risk, so under precise probabilistic knowledge. So if we have a precise probability measure on the states, and we also have a cardinal scale on the consequences, so the agent's preferences on the consequences can be described by a utility function that is unique up to positive linear transformations, then we can define the choice functions by simply selecting all those acts as optima, which maximize this expected utility with respect to this pair pi and u. And obviously, this is a strongly interpreted choice functions because all the acts in the choice set have equal expected utility. And the other extreme, in a certain sense, would be first-order stochastic dominance, where we still need, at least in this version, a precise probabilistic knowledge. But the structure on A is not given by a cardinal interpretable utility function, but only by a pre-order of the consequences. And in this, here, we can use first-order stochastic dominance to define the following choice functions. We simply select from D all those acts that are not strictly expected utility dominated for one, and expected utility dominated for all functions U, which are isotone mappings of this pre-order you induced. So in words, we choose all the acts which are not excluded by every compatible expected utility maximizer simultaneously. And obviously, this is only a weakly interpreted choice function because in general, the acts in the choice set will be incomparable or could be incomparable with respect to first-order stochastic dominance. Okay, let me exemplify this even further on a very simple example. So suppose we have an easy decision problem involving 3 different stocks we can choose, and the consequence these stocks pay out, for example, depend on an economic scenario, for example, recession, inflation, stagnation, or something like this. Then we could summarize this problem in this small consequence table here, assigning each pair of act and state some consequence, and just for simplicity, assume that we have uniform distribution on the states here. Then, if it happens that the agent can rank the consequences of this problem or describes her preferences on the consequences by a cardinal utility function, so function that is unique up to PLTs, then one could simply transform the consequence table in a utility table. And due to this uniqueness class of the utility function, maximizing expected utility would be well defined. And here we could apply this expected utility rule to find X3 to be the unique optimal stock. So we can give here the strong interpretation. Okay, another setting would occur if we found that the agent can only pre-order so the consequences from A. Then we would have to stick with our original consequence table and would, for example, have some order structure on the consequences, which could look, for instance, like this Hasse graph here. So A1, A2, A3 being incomparable, but all better than A4, A5, A6 being incomparable, but all better than A7, A8, A9 being incompatible. So, and now, of course, every function which is isotone with respect to this Hasse graph here would be a compatible scale, and this would make expected utility not well defined in this setting, but we still could apply first order stochastic dominance, but we would find that the choice set of our decision problem is the decision problem itself. So none of the stocks could be included. We only would have the weak interpretation. And the idea is now that we to make more efficient decision or more information efficient decisions, which are still which still have justifiable assumptions, it would be of high interest to be able to formalize situations between those two extremes. And this is what takes me to or motivates me to present something about what we call weakly structured information to you. Okay, so maybe first things first, let's briefly recap the classical assumptions of decision theory we implemented up to now. So the first would be that one assumption could be that the agent's preferences among the consequences can be perfectly characterized by a cardinal utility function. And the other would be that the uncertainty among the states is describable by some classical probability measure. And recall that expected utility rule relies on both of these assumptions, and stochastic dominance relies only on the second one, but not on the first. Okay, and the problem is that both 1 and 2 rely themselves on strong axiomatic assumption. So most classically, the cardinal utility function, for example, on the axioms of von Neumann-Morgenstern, or the assumptions about the probabilities on De Finetti's framework, or if you want to formalize both of them simultaneously, then they rely on Savage's P1 to P7 if you want to. And together, these assumptions explicitly dismiss a series of interesting applications. So, for example, agents with purely ordinal or partial preferences, or agents with partial probabilistic beliefs, or certain problems of group decision making. And the point is that even from a purely or genuinely decision theoretic perspective, these are highly relevant situations to investigate and would be desirable to formalize situations in between somehow. And in today's talk, I want to address explicitly 2 different sources of weak structure, or 2 different sources of complexity. First, should not surprise you, because we're in a in a seminar series on imprecise probabilities. So first would be to relax assumption 1 by allowing for imprecise probabilistic models, so sets of probability measures on the states. For example, if you have just an expert who can give probability constraints on the economic scenario, on the example from before, we could simply collect all the probabilities, classic probability models compatible with these constraints and work with this as our new uncertainty model. And geometrically, this means moving from one point in the unit simplex to some subset of the unit simplex in our uncertainty model, for example, as depicted here, to some convex polyhedron in the unit simplex. And the second relaxation is we want to allow for more complexly ordered consequences. So cardinal utility is very restrictive, but only a pre-order, maybe 2 less assumed. And for example, we would be interested to formalize situations like this here. So we have still only a partial order on the consequences, but we can give some intensity statements about certain edges. So for example, the green edges represent more intense preferences than the red edges or something like this. And we want to have formal models to capture also these informations on the agent's preferences. Okay, and we start by, or I start by, and these models will then in general also give rise to sets of utility functions rather than single utility functions, but these sets will be considerably smaller than the utility representation sets of all isotone functions with respect to the partial order. So this is the main part. And I start to give you the formal model on how we do this relaxation of 2 to 2 prime. And this will be what Georg also already mentioned, will be preference systems. So preference system is a pretty simple structure, simply a triplet consisting of our original consequence set A from before. And instead of assuming a cardinal utility function, we now assume we have 2 binary relations. The first, called R1, a binary relation on the set A itself, and the second, R2, a binary relation on the binary relation. And this triplet then is called a preference system, and here's the interpretation. So R1 is a usual desirability relation, so AB and R1 just means that A is at least as desirable as B. And R2 is a desirability relation on the exchanges, which means, or is interpreted that AB, CD is in R2. This is interpreted as exchanging B by A is at least as desirable as exchanging D by C. So the preference of A over B is more intense than the preference of C over D. So R2 allows us to give partial statements about cardinal utilities, so to say. And as we intend to generalize the notion of a utility function of we have the following consistency criterion for preference systems. We call a preference system consistent if there exists at least one utility function which is isotone with respect to R1 and isotone with respect to R2 in the differences. And our complex or our generalized preference model will be then the set of utility functions UA satisfying these 2 constraints. Let me give you a short example. It's an old example, but it's good to illustrate. And suppose we have an agent who is looking for a new job, and the agent intends to compare the jobs with respect to the salary after tax and the offered additional benefits. And the following additional benefits are relevant to our agent. So we have, is there overtime premium? Is there childcare? Are there advanced training possibilities? Are there promotion prospects? And does the offer have flexible hours? And then the consequence set would be some subset of the positive reals times the power set of this benefit set. And on this set, we now can very naturally define a preference system. So R1 is obvious. We say job offer 1 is better than job offer 2 if it has, or is at least as good as job offer 2 if it offers at least as high salary and offers a superset of additional benefits. But we can use this cardinal component, so this component of salary, to even define an R2. So we say the exchange of job offer 1 is more desirable than the of job offer 2 by job offer 1 is more desirable than the exchange of job offer 4 by job offer 3 if the first exchange has a higher increase of salary, and second, the additional benefits are nested in the sense you see here before. So in a way, we have if the ordinal dimension, so which is ordered by set inclusion, cannot possibly contradict this information, then we are allowed to use the cardinal information. And this gives us a preference system with a set of utility representations which is strictly smaller, which is a strict subset of the set of all R1 isotone functions. Okay, and so this is for our generalization of so for 2 primes, so for description of generalized utility function, and the second how we generalize the precise probability on the states is by considering credal sets, and here we consider credal sets which are induced by lower and upper bounds for a finite number of by lower and upper bounds, expectation bounds for a finite number of random variables on the state space. This is quite general, so it involves, of course, classical probability intervals, but also Weichselberger's interval probabilities, Coveland-Menges, linear partial information, and also certain types of lower provisions. So this will be our uncertainty model. So I have no example here because I think most of the people know more about it than me. So okay, and here some hints to literature. So we have worked on criteriology for optimal decision making given the sets U, A, and M, and also for efficient computation algorithms in this first paper here. So if you're interested, go read it. Yeah, and we worked on how we can information efficiently elicit preference system in order to ask as few as possible questions, as few as possible, as simple as possible questions to come to an optimal decision under severe uncertainty in the second paper here. But this will be is not today's focus. Today we focus only on one specific choice function introduced in this first paper here, namely generalized stochastic dominance. And the idea is very, very simple. So it's a very straightforward generalization of stochastic dominance. So consider we have a preference system on our consequence space, and we have a credal set on our state space. Then for certain acts, this is simply some technical condition, don't care about it. We can say that X, AM dominates Y whenever the expected utility of X is better than or greater or equal than the expected utility of Y for any scale compatible with the underlying preference system and any credal member, so to say. And this relation is called we call it generalized stochastic dominance relation, and completely analogous to first order stochastic dominance. This relation induces a choice function by we simply select all the acts from D for which there exists no acts that strictly GSD dominates it. And this choice function here will be of some importance in the third part, in the applications. So yeah, this is full stop. Okay, and we have this relation has also some prominent special cases. So if we have precise probabilistic knowledge and R2 being the trivial relation, so no cardinal information, this reduces just to first order stochastic dominance. So this is why it's called, is it truly a generalization of stochastic dominance. If we still have precise probabilistic knowledge, and R2 and R1 interplay in a way that guarantees that the utility representation class is unique up to positive linear transformations. Such situations are axiomatically defined or characterized in this Foundations of Measurement book by Kranz and co-authors. Then our criterion reduces to comparing expected utilities. And if M is a non-trivial Creedle set and R1 and R2 still guarantee a unique utility, then this reduces to what I found to be called Booley dominance, but it's simply point-wise expected utility dominance for every measure in the Creedle set. Okay, so these are the special cases. And now I want to turn to how we can utilize this decision framework under weakly structured informations in problems of statistics and machine learning. Yeah, so we are now in at first glance, completely different setting. So we are now considering statistical problems. And yeah, first things first. So what follows is not work only by myself, but with several co-authors here from Munich. So Thomas Augustin, Hanna Blocher, Malte Nahlenz, Julian Rodemann, and Georg Schollmeier. And it is mainly based on these 3 papers here. So the first is freely accessible via the UAI homepage. The second is freely accessible via the JMLR homepage. And the third paper is still under review, but if you are interested, you can text me and I'd be happy to send you some preprint of it or something. Okay, so some motivation. So this is a mathematical argument in a sense. So the first claim is that statistical methods are usually tailored for data situations that can be clearly assigned to a standard scale of measurement. And the second claim is that non-standard data can often not be clearly assigned to a standard scale. And by 1 and 2, it is implied that statistical methods are often not well suited for analyzing non-standard data. And from this simple argument, we had the idea to use the notion of a preference system to model data with non-standard scales of measurement. So with scales of measurement which do not correspond, sorry for the typo, to one of these extreme poles. Okay, so maybe let's first very briefly recap the standard scales of measurement. So consider we have a random variable mapping to our set A, which is now no longer a consequence set, but it is interpreted as some sampling space. But then we call A, respectively X, of ordinal scale if the structural information on A is given by a preorder. And in this sense, the set of all isotone functions as a whole represents the structural information on A, and consequently, any analysis of our variable should be invariant under the choice of the candidate scale. And the other extreme would be that the order is induced by some metric, and then we call A of cardinal scale. And then there often exists some scale U star, which is unique up to transformations that are irrelevant for the application intent. And in these situations, then any analysis of the variable X can be based on our scale U star alone. And the observation or motivational question is, what if the structure on A does not belong to either of these extreme poles? So in other words, what if the structuredness of our sampling space A varies along its subset? And we found that a preference system is perfectly suitable to formalize this intuition, because we simply collect all the ordinal information in our relation R1. We collect all the cardinal information in our relation R2. And then we find A to be locally almost cardinal on subsets where these two relations are very dense, and locally at most ordinal on subsets where R2 is sparse or even empty. Okay, and this allows us to describe a certain type of non-standard data, and this is a quite broad class, as we will see later in the applications. But first, beyond the expressive power of these preference systems only also offer a nice way of regularization of statistical problems. So for the moment, think of your preference system of not being the true underlying preference system, but an empirical preference system that is spanned by a preference system valued observation of certain variables. Then, as usually in statistics, we do regularization to avoid overfitting to the sample. And here we could say we want to, if we work with these empirical preference systems, we want to regularize because we want to, in an intuitive sense, avoid that the empirical preference system is taken too serious in the later analysis. And a very straightforward idea to regularize in preference system is by means of regularizing the set of representations. So if we have, which is not a strong assumption, R1 and R lower and upper elements, then we can, in the first step, look at the normalized representation sets. So we take all utility representations of our preference systems, which are normalized, and then we can reduce this set by choosing a threshold delta and only considering those utility representations that assign utility preference, strict utility differences above this threshold. So in this way, we avoid utility representations which are too close to the empirical system and not and maybe not very suitable for the true underlying system. So this is the idea. And in general, there would be two different ways for regularization. I just explained you the right regularization side here of this graphic. Another way would be to manually add expert constraints to the preference system, which is an interesting topic for itself, but not the topic of today's talk. So we're only on the right side of this regularization. Okay, and now, after this was a brief excursus to regularization, we will need this later, we can come back to the actual goal. So suppose we want to stochastically compare random variables mapping into a preference system. So we want to define some meaningful stochastic order among preference variables, random variables mapping into a preference system. And the challenge is that we have epistemic uncertainty, so the ML type of epistemic uncertainty, in form of first approximation uncertainty, in the sense that usually in statistics we only will have samples of the considered random variables rather than their distribution. And we have model uncertainty in the sense that we do not know the cardinal scale, but we only have a set of potential of candidate scales, so to say. And any meaningful stochastic ordering should address, or any meaningful comparison framework for such random variables should somehow address both these uncertainty types. And for the second one, it is very clear how we can do this from our previous considerations. We can simply use the GSD relation we had, and here we even use a precise version of this GSD relation, because up to now there's no imprecise probability involved in the statistics part. So we just say that a random variable X is dominates random variable Y if the expectation is at least as high for every compatible scale. And this will be a stochastic partial or pre-ordering among random variables, which addresses this model uncertainty part. But what about the second part, the approximation uncertainty, and the practical problem that usually we do not have pi, but only IID samples, for example, of our variables? Then the usual way to approach such a problem, to nevertheless be able to make some inferential statements about comparison among those variables, would be to perform a statistical test for GSD. And yeah, we propose to do this, but this has some subtleties to manage. So the ideal hypothesis pair for such a test would be the first one here, this ideal hypothesis, where the question of actual interest, namely GSD dominance of X over Y, is in the alternative hypothesis. But it turns out that the null hypothesis of this test is too broad to analyze the distribution of any test statistic in a meaningful manner. So we have to make do with these pragmatic hypotheses, where we do not have the actual question of interest in the alternative hypothesis, but a slightly modified one. So we have y is not dominating x, so it could be x is dominating y, or incomparability. And to mitigate this effect that there could also be incomparability, we then simply perform the same test, which I will detail later on, with the variables in reversed rows. And if the p-values of these reverse tests are very, very, very large, then we can say with a certain plausibility that incomparability cannot occur. Okay, so we go on with these pragmatic hypotheses, and how can we test this? So the first, how can we design a test for this hypothesis pair? The first part would be to find a good suitable test statistics, and a test statistic can be found by making the simple observation that x is dominating y if and only if this infemal expectation difference here, d, capital D of xy, is greater or equal than 0. And so a natural test statistic for our test could be the empirical version of this test statistic, which is called small d xy. So you don't have to care about the detail. This is just we replace integrals by sums and preference systems by observed preference systems. Okay, and this could be a good test statistic for our test. But this test statistic cannot measure the extent of GSD in the sample. So it might be too little sensitive. And here is where regularization comes into play. So we go to the previous slide again. Here we have this dxy, and now we have this d epsilon xy. And the only thing that changes is now that we take the infimum, not over the all representations of the observed preference system, but only over the regularized representations of the observed preference systems. Okay, and we will have in our example both the unregularized and the regularized test statistics, and we will see the difference. First, for the computation part, the good news is that both these test statistics can be computed by linear programming, and so this computation of the test statistics at least is doable. So we have hypothesis, we have a test statistic, now we need a testing scheme. So we assume that we made IID variables. So note that basically exchangeable observations would be enough, but let's go with these IID variables. And now how could we design a test? The problem is that we are in a completely non-parametric setting, so we cannot analyze the distribution of our test statistic analytically. There's no chance for this. But the good news is that our null hypothesis has as a worst case distributional equality of the two variables of interest. And this allows us to perform a permutation test, and this permutation test will us give a valid level hypothesis. So this details about the resampling schemes are just for reference. I won't go into it. So this is how the resampling scheme of the permutation test looks, but we can do a worst case test, so a conservative test for our pragmatic hypothesis pair based on the permutation test. And this is good news, but it still relies on the assumption of IID variants or exchangeable variants. And this is the first time in the statistics part of the talk where imprecise probabilities come into play. Because we use the rough idea is now we want to make this test less reliant on the IID assumption by using creedal sets. And a bit more concretely, the idea is we allow that our samples are potentially biased. Our samples of the variables are potentially not IID but biased, in the sense that we only assume that the true empirical laws, which the permutation test is based on, lie in some creedal neighborhood around the observed empirical laws. And we can then adapt the resampling scheme I jumped over before by simply replacing the test statistics in the observed sample by the infemal version over where the infimum was taken over all pairs of measures in these empirical creedal sets. and we can replace the test statistics in the resamples by the supremal test statistics. And this results in a test which is conservative but still valid, still a valid level alpha test under contaminated samples, so under deviations from the IID assumption. And the problem is, of course, how can we compute those things? Because this might be arbitrarily complex if the involved Creedle sets become complex. But what we found is that for a very practical, relevant, yet simple class of Creedle sets, namely contamination models, and this is doable. And so contamination models, for all those not familiar with, are just, so I take the central distribution as my observed contaminated empirical distribution, and I say with a probability of 1 minus gamma, this is the true distribution, and with a small probability of gamma, the data can be distributed by some arbitrary probability measure. And so both of our neighborhood models for the empirical distributions, we now assume to be gamma contamination models. And what we can show is that then the observed p-values of our test can be written as a function f epsilon gamma, where epsilon is the regularization strength and gamma is the contamination degree. And we can express the observed p-values of our test, of this robustified test, as a function of gamma and so of the contamination size and the p-values of the original test. Okay, so we have a way to perform robust statistical tests based on imprecise probabilities, or to look how sensitive our test decisions are under deviations or contaminations from the IID assumptions. And this takes me to the first application, where we considered a very special class of preference systems, namely differently multi-dimensional spaces with differently scaled dimensions. So this is somehow similar to the job seeker example. So we consider we have some subset of the reals to the power of R, but we assume that we can only interpret the first 3 components, dimensions of this space, as cardinal, and the remaining ones as purely ordinal. And just as in this job seeker example, we can use this information to define a preference system, namely setting R1 to be component-wise dominance, and R2 to be, we add a constraint between pairs of pairs whenever the ordinal dimensions do not conflict, and the cardinal dimensions represent this intensity. So just the same idea as in the job seeker example, in a way. And this is also just for reference. We, in the CUAI paper I showed you, we neatly characterized this GSD relation over this special type of preference system. This is just if you are interested, and read the slides again or something. But I want to show you the concrete application. So what we did is, inspired by Sen's capability approach, which says that poverty is a multi-dimensional concept with more facets than just income or wealth. We did a multivariate poverty analysis, and in our example we operationalized poverty by three variables, 2 ordinal, 1 numeric, namely income is numeric and health had 6 levels and education had 8 levels. And here's an example for a pair of vectors in the space, which is comparable with respect to our relation R2. So we have here star. The star exchange is more desirable than the heart exchange, because these ordinal components here are nested, and the differences of the cardinal component represent this. So in this way, it is constructed. And what we now did, we used the Albus data, or subsamples of 100 men and women each, to perform our GSD's test in this setting. And here are the test results. So from bottom to top, we see the test for more and more regularized test statistics. And here's, so not all tests are significant, but all tests for from 0.25 are significant. So this is a typo here, but you see the influence. So a test is significant if this hill, intuitively speaking, is left of the observed test statistics. So this is the distribution of the resampled test statistics. And you see that the influence of the regularization, the fully regularized test so the test with the fully regularized test statistics is very, very significant, and the regularization has the effect that it smoothens the distribution over within the resamples. Okay, so we found for the regularized test, it is indeed more sensitive for the question of actual interest, and we found even significance here. And yeah, and then we did this robustness analysis. So this is these are let me explain these curves. So I showed you that the p-values can be written as a function of the contamination size, and here you see this one test here, the unregularized test is not significant, but let's have a look at the dark blue curve here. So this is the fully regularized test statistic. We see that this test ceases to be significant from a contamination size of approximately 0.008, which corresponds to approximately 2 data points, which means our statistical test would still have been significant if 2 of the observed samples would be redistributed in any arbitrary manner. Okay. Or in the other sense, we could see how strongly we could perturb our sample such that the test statistician would still be significant. Okay, so this was for the first application. Second application is similar, but in the context of classifier comparison in machine learning. So here the question of interest was, how can we utilize our decision theoretical approach under weakly structured information for statistically comparing classification algorithms with respect to multiple quality criteria on multiple data sets simultaneously. And we need some additional notation here. So we have calligraphic D is the set, so the universe of all potential data sets in the problem class under consideration. And calligraphic C is a finite set of the classifiers under investigation, and we have a family of quality measures assigning each pair of classifier and dataset a quality measure, and we compose this family to a multivariate, to an R-dimensional quality criterion. And as you might guess, we now again have the interpretation that the first set of these criteria are of cardinal scales, so difference may be interpreted, and the remaining ones are purely ordinal. Differences are meaningless apart from their sign. So this could be something like some interpretability score or something like this. Okay, and now let me show you briefly the 3 levels that can occur when comparing classifications algorithms or some other algorithms in this setting. So first of all, the first level is that already on one data set, you could have conflicting quality measures, so inducing incomparability. The second level is, even if on the one data set you have a perfect dominant structure, on another data set, the dominant structure could be reversed. And the third problem is that even if on all data sets in your concrete sample, so in the concrete benchmark suite at hand, you have a perfect dominant structure, this could completely be destroyed as soon as considering another sample, another benchmark suite. And what we wanted to do is to give a classifier comparison framework that addresses all these problems here simultaneously. And we again found that this decision-making framework under weakly structured information is perfectly suited for this, because we can simply embed the range of this multivariate performance metric into the preference systems we saw in the previous application. Because we have again the structure of Z cardinally structured things and R minus Z plus 1 ordinally structured things. And the idea is then to interpret the data sets as realizations of a data set valued random variable, and to associate with each classifier the random variable mapping to the quality vector of this classifier under the randomly drawn data set. And then we can simply lift the GSD relations from comparing random variables to comparing classifiers by calling C dominating C prime whenever there's GSD dominance among the associated random variables. And this is the whole idea. And for this, we looked at, for this dominance relation among classification algorithms, we looked at two concrete sets. The first one is the so-called GSD front, which is simply the set of a set of classifiers C, which is simply all the classifiers for which there is no other classifiers strictly dominating it with respect to the dominance relation just defined. So in other words, the GSD front is nothing else but the choice function induced by GSD applied to the random variables associated with the different classifiers. And the second set of interest is the empirical version of this GSD front. So if we have only observed preference systems, so if we only have IID copies of this data set valued random variables, then we can still define an empirical version of our GSD front by simply collecting all those classifiers which are not empirical dominated in the sense that these test statistics from before have to show this. And the only subtlety in this definition is this row here. So these are not the empirical undominated ones, but these are the row almost empirical undominated ones. And this has a technical reason. And the technical reason is that we have for this version of the empirical GSD front a consistency result. Namely, we can show if the set of utility representations of the concrete underlying preference system is not too complex in the sense of having a finite Wapner-Cherenkes dimension, then we can show this this empirical GSD front to be a consistent set-valued estimator for the true GSD front. Once you choose these rows here such that they converge not faster than a certain class. Okay, so we can show that this then is a consistent estimator, and so the empirical GSD front is a good thing to work with in a certain sense. But this is only the thing for the first inferential statement. Of course, we also wanted to have tests in this context. And so the goal would be to compare multivariate mixed scales quality measure of a newly developed classifier with the sets C of classifiers which are considered state of the art. So as a test question, we wanted to develop a test which tests if our for example, newly developed classifier is in the GSD front, significantly in the GSD front of some state of the art classifiers. And the cool thing is that if we just equivalently rewrite this zero or null hypothesis here, we found we can write it in this way. And this rewritten version of the zero hypothesis is true if and only if we can reject all these surrogate hypotheses below H0 C prime, which states that C prime dominates C. So in this, so we can say the global null hypothesis is false if these surrogate hypotheses are false for every classifier C prime. And we can, the good news is for these local pairs, we already developed the test. We have seen it in application 1. So we can test this global hypothesis above by simply running all these tests and reject the global hypothesis whenever all the local hypotheses are rejected. And the cool thing, as we here switch the roles of the testing again, this even we can even show that this gives a consistent statistic. Okay, and now to the application. So we use the OpenML benchmark suite or 80 binary classification data sets from here. And our example was that we wanted to compare the SVM, support vector machine, playing the role of the newly developed classifier. It's a bit ridiculous, I know, but just for the example, with the state-of-the-art classifier, random forest decision tree, logistic regression, elastic net, XGBoost, and KN. And we composed our multivariate metric out of predictive accuracy, computation time on test data, and computation time on training data. And as the computation times strongly depend on the computing environment, we treated in the application the time-related metrics as purely ordinal. And so the first thing is we found the following Hasse graph here of the empirical GSD relation. So the 0 empirical GSD front under these 80 data sets would be the blue shaded classifiers here above. And we also performed our test. This is a similar graphic as we saw before. And in a nutshell, we found that SVM is in the GSD front of KNN, XGBoost, random forest, and GLMnet, so elastic net. Okay, and we found this statement to be significant for alpha 0.05. Okay, and again, we could do the analysis of how our test decision develops under contamination of our samples. So in this sense, of our benchmark suite. And here we have not directly the contamination degree on the x-axis, but the number of contaminated data sets. And we see that the first test that ceases to be significant is SVM, again, the elastic net. And it's here for approximately 7 data sets. And as we have to do all these tests, this simultaneously, here the global test would also cease to be significant. So we can say our test decision that SVM is in the GSD front of these 4 classifiers would still be significant if 7 out of 80 classifiers would have been distributed in some redistributed in some arbitrarily chosen manner. Okay, so this is from my side. So as a summary, I presented a framework for decision making under weakly structured information and demonstrated how this framework can be utilized in applications of robust statistics and machine learning. And what is next for me is to exploit other problems fields where this decision theoretic perspective might be fruitful. And I'm very happy to, if you have any hints or comments for me. And I thank you really very much for the attention. And yeah, I'm happy for questions. And I hope I do my best to answer.